Hey guys, how's it going? In this video we're going to go over 3 worked examples to show you how to do problems involving diffraction and wavelength. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get started. Question 1 says a plastic block is placed in a ripple tank as shown below. Complete the diagram to show the pattern of the water waves beyond the plastic block. So there's our water waves, which are the straight lines, which remember are called wave fronts, and they represent the crests of our waves, and they're coming in towards this plastic block. And when these water waves come towards the plastic block, which is like an obstacle in this case, they're going to diffract around the obstacle. So to draw a diffraction diagram here, we want to use equal spacing between the wave fronts, so we want to keep that going for the waves that we draw. And we need to show as well that the waves are going to bend more and more as they get further away from the plastic block. So you'd want to sketch something like this. Now note that the diagram should show consistent wavelengths before and after the plastic block. In other words, the spacing between these wavefronts needs to stay the same, and we can label that as the wavelength lambda, because remember these waves represent the crests of our waves. And you'll see that the wavefronts here have mostly straight lines, but then there's increasing curvature on the ends of the lines. Notice how it's only the lower ends that are curved. Question 2 says waves travel towards the entrance of a harbour as shown below. Complete the diagram to show the pattern of wave crests inside the harbour. So this time we've got the crests of our waves or wave fronts passing through a gap rather than around an obstacle, which we saw in question 1. And so for this diffraction diagram, again we want to keep the spacing between the wave fronts the same to show that the wavelength is constant. However, because the waves are passing through a gap, it's not just going to be one end that's going to be curved, it's going to be both ends of the wave fronts that become curved. And again we're going to show increasing curvature as we get further away from the gap. So you would want to sketch something like this, where again, note that the diagram should show consistent wavelengths before and after the plastic block, so we're trying to keep the spacing between the wavefronts the same. And again, notice how the wavefronts are mostly straight in the middle, and then it's just the ends that are curved, and we're showing the ends of the waves getting more and more curved as you get further away from the harbour wall. And we can mark on the wavelength to show we're keeping that distance between the wave crests the same. Lastly, question 3 says explain why a house located behind a hill might receive a better radio signal than TV signal. Justify your answer using a labelled diagram. Well, let's start with the diagram, and we're going to split this into 2 parts. So we're going to have the TV waves on the left and the radio waves on the right. And we're going to sketch a house located behind the hill in each case. Now starting with the TV waves, we're going to show our wavefronts or straight line waves coming in towards the hill. And remember the distance between 2 adjacent wavefronts or wave crests is the wavelength, so we can mark that on as the wavelength. So we want to keep this spacing between the wavefronts constant as we draw our diffraction diagram here. Now we can continue our straight lines to the hill and beyond, and notice how I'm now just drawing the straight line parts which are going towards the top of the hill. And then we can start adding curves onto the end of the wavefronts here to show the diffraction taking place. So notice how the waves become more bent as they get further away from the hill. Now we've just sketched the diffraction diagram for TV waves, which have a slightly lower wavelength than radio waves. So let's show how the diffraction diagram for radio waves will differ. Well, first of all, we need to show a bigger distance between 2 adjacent wavefronts because we're saying that radio waves have a larger wavelength than TV waves. So we can label on that wavelength there to show it's larger than the wavelength for TV waves. And then we can continue our waves going to the top of the hill and beyond, and again just drawing the straight line parts first, and then we'll add the curves onto the ends. So if we add the curves on now, you can see that we're getting more and more bending of the waves this time. And again showing this increasing in the bending as we get further away from the hill. Now comparing the 2 diagrams side by side, we can see that the radio waves are going to reach the house a lot better than the TV waves. And to explain this, we can say that radio waves have a slightly longer wavelength than TV waves, which we've already shown. And you should also know that longer wavelengths diffract more than shorter wavelengths. So that's why we've shown more bending, more diffraction for the radio waves than for the TV waves. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.